So next up we have Christodoulou.
All right. So I was asked for this talk to give a high-level presentation of what we do in my group, which I took to mean that I will just have drawings, mainly, in the talk. And I will cite nobody, also, except my papers, the ones from the past year in particular. So there is almost no context. And about the group, it's pretty new. It's 1 year now. Ofek is second year PhD, and Sarah is finishing her master's. Andrea is about 1 year and a half now as a postdoc, and Maria just arrived last week. I'm very, very happy about it. It's been a challenge starting a new group. It's a big step. And the principle I followed in forming the group was to hire people that are smarter than me, which is great because then they're very good. Downside is that I feel stupid sometimes. But I'm trying to deal with that. And the maxims that I follow are pretty much these quotes that quantum mechanics is meant to be counterintuitive, if you want, and we don't really know what we're doing. And so this is going to be the spirit of the talk too. It's going to be confused, which I imagine fascinates you. So what's this business of tabletop quantum gravity? Well, it's quantum gravity is pretty much, not only, the idea that Einstein taught us that matter sources a space-time geometry, and so quantum matter should be sourcing a quantum geometry. And this idea is there without thinking about what's going on at the center of black holes, without thinking what's going on at the Big Bang, without thinking what's going on at high energies. And so the idea is, okay, let's forget about all that. Let's go to the earthly Newtonian regime and think what happens when we put quantum matter in superposition and try to detect that, which started all this business of, maybe we can close the light or something, because I have these black slides. Yeah. Which started this business of, let's put two masses in path superposition. They're gonna, the Newtonian potential, if you want, is going to be in some sort of superposition. And I've been making the point that this is really a superposition of spacetimes. As striking as it sounds, when they do this experiment, we would be able to claim that we have set spacetime in a superposition in the laboratory. And this has been somehow remade in a series of papers, the two most recent ones here, and another one I'm going to talk about just in a moment. So, following up in this discussion, the next thing we wanted to look at, this was with Ofek, who has done a lot of work on this, was, and something that Marcus Aspermeyer talked just previously, is to, instead of having discrete variables, so instead of putting paths in superposition, to have oscillator states. So these are continuous wave functions. However, you can think of the path degree of freedom being in a continuous superposition and analyze that situation with a path integral in a covariant formalism. Make again the point that this is going to be now a continuum of spacetimes in superposition. And in addition, we were able to verify that these are radiation-free geometries, so whether you put accelerated trajectories or not, so I will come to this in a moment, you get the same result in the entanglement in a generalized protocol where you have two Gaussians in superposition. So this is pretty much both the idea of having the path degree of freedom and having the delocalization. And the main takeaways is that you get the same interpretation, spacetime in superposition, and you see clearly that the delocalization of the wave packet or the distance between two paths is really playing exactly the same role physically, which we used very recently in an idea to detect tiny black holes, which could be what dark matter is. Let me say that an important point, which you should keep in mind, is that Feynman's idea that was cited also previously was to put a mass in superposition and see that a test particle would go in a superposition of trajectories. So this was about detecting the fact that the gravitational deflection would be in a superposition, which is not what is the idea in the modern discussion about mediated entanglement. It's very easy to put down the numbers that people talk about for doing these experiments, calculate what the deflection would be using Newton's law, force equals mass acceleration, and you see that the deflection would be in fact minuscule, 100 times less than an atom. What is going on, because you have entanglement, is that you are looking at the entangling phases, which do not see this deflection. Now, you can use this idea also for Josephson junctions, where you have a delocalization of the wave function across the junction, and say that if a Planck mass particle passes and you stack many, many, many of those, like a billion of them, you're going to get a tiny current because of the interaction of the electron mass with the mass that is passing. But if you put enough of them, then you could actually get a measurable signal. And this is something that goes back to a story I was doing in my PhD with many other people. There's many papers. You could see this recent paper, which is very technical about loop quantum gravity, but see the citations in it, predicting that, suggesting that maybe what dark matter is Planck mass black holes, which would have about a Planck length in size, and so would pass through everything, but they would still interact gravitationally as strong as a dust particle of Planck mass. So you could be able to detect these things. So this is one path in which thinking about mediated entanglement produces new ideas. This is about detecting dark matter. Another direction that is interesting is thinking about protocols that do not involve entanglement. There's a previous work by Richard Hall and others, including myself, of detecting non-Gaussianity production in Bose-Einstein condensates. We're working on something now which is about detecting quantum gravity corrections in thermodynamical observables, which is pretty promising, I must say. That's with Bose-Einstein condensates as well. And I think the direction that the field is going in this, let's say, subdirection is to think of superfluids, because naively you will get a very big magnification due to the significantly larger mass density. Bose-Einstein condensates are the simplest things to play around, mathematically speaking. But obviously one should think about superfluids, and there's a few ideas being discussed with Sugato Bose, with Richard Hall, and also with Brigitta Whaley. There's nothing really that has come out clean so far, but I suspect a few things are going to come out from various people with superfluids. Another completely different idea is to think of superposition of rotations, which is something we're doing with Andrea and Gerard Higgins, who is the main person pushing this, which is to take into account that rotational energy gravitates, to use this fact and create a superposition of masses, which is something that is also unique to gravity. You do not get superposition of charges in electromagnetism. And this also includes the speed of light in a substantial way. There is a genuine relativistic effect. It's pretty difficult as an experiment. How difficult? Well, let's see. We should have some sort of answer in a few months on this. So Okay, so where is this going? I started doing my PhD with black holes, with hard, non-perturbative quantum gravity. Everything I've talked about pretty much you can think of as superpositions of Newtonian potentials plus the mass energy equivalence. Is there something more exciting to come? Well, I don't know, maybe. I think we should be thinking about non-perturbative effects like time discreteness. I have a couple of very speculative papers on this, but I still think there might be something there. And also effects that are only specific to gravity, like superposition of mass, the fact that there is no dipole and no screening allowed. There is a cute idea out there by Igor Bykovsky and others about the photoelectric effect, the analog of the photoelectric effect of gravity in gravitational waves. We shouldn't lose hope that maybe there's going to be something more to see. It's going to be difficult, but the main point, and I think the reason many people here at IQOQI and around the world are interested, is because these ideas, because they're in a sense simple, also allow to clarify and revisit various conceptual issues, like what is a subsystem, what is locality, what are degrees of freedom, what are reference frames, and what are observables. So let me quickly say how you can go from this tabletop quantum gravity story to these issues. Sketch one path. So it starts from the effort to have a theory-independent line of argument for the non-classicality of the gravitational field, which is this idea that if you have two systems interacting only through a middle system, the mediator, and they become entangled, then the thing in the middle cannot be classical. Given that GR is a classical field theory, this would falsify GR in a theory-independent way. It would, hopefully. And the way people hope to make this work is similar to the Bell case, where essentially you have some property which is correlations, entanglement, which you want to check with the experiment, and then you want to push yourself into a dilemma where you're going to drop something that you really want, or both. And typically here you would drop, you would want to keep free choice, and you would drop local realism. So the idea for mediated entanglement is to force one to drop, to keep locality of interactions and drop classicality. Now the problem that you have when you see these theorems and how they work is that it's not clear what is meant by locality, which is why we went to this effort, which, this paper, which was a letter, clarifies this a lot, where we show that entangling phases are, first of all, actions. They are covariant actions of a local field theory if you're working with a local field theory, and so they're going to respect space-time locality. They do not build instantaneously. And so it's not really just the potential there, which is instantaneous, the Newtonian potential. However, still, this does not finish the story, because it's not really the locality that people are talking about. They are assuming something else, which is subsystem locality. And in this recent paper, which is mainly, the calculation is mainly due to Andrea, it took us a long time to figure this out. We could show that microcausality of quantum field theories allows you, under a certain set of approximations, which is more than suitable for this regime, to really write down the evolution in a subsystem local form, where you have boxes that never touch both matter systems. And this really allows you to have the definition of the mediator, in the sense that these no-go theorems want to do that. The idea is that you can split in many, many intervals where the sources are at space-like separation, and at each such interval you get the subsystem local decomposition, and at each such interval you get the boxes to commute as well. Where this is going is essentially putting QFT on a quantum circuit, and something we're working on now is to generalize this, bringing together algebraic quantum field theory and general probabilistic theories. Let me quickly say now how this goes into the degrees of freedom, and what are degrees of freedom. We try to do this with a silly argument. So imagine that you have a chain of spins, the orange things, quantum systems, which are interacting in some way that has a delay. All right, there is some finite time t so that each pair can interact. And you send some influence from the left, and it's going to go to the right. Quantum information is not going to pass through a link C here in the middle that is classical, because it doesn't fit in some sense. Now, let's send now the delay to 0, all right? So now I have action at a distance. I have an influence from the left, doing something on the right instantaneously. But it seems that still quantum information is not going to go through, right? While classical information will. So in this sense, why do we even make such a fuss about locality and assuming locality? It isn't really about locality. It is about whether you have something classical in the middle or not. But the thing is that locality is related with the question whether you have degrees of freedom to begin with, whether there is a mediating subsystem. And let me sketch this in a silly way, which is you take Poisson's equation, that's like Newton's law, in vacuum, and you see that there is a unique solution, right? So in this sense, we say that this potential doesn't have a state space, so it doesn't have degrees of freedom. And then you put the wave equation, so you add a second time derivative over Minkowski space, and then suddenly this thing has a whole life of its own. You can basically have any arbitrary function you want here, any sort of waveform that is propagating so long as it remains massless is going to satisfy this equation. So phi is now a thing, it's a field, right? So now you have degrees of freedom. And naively, think of it this way. This is your wave operator. If you send the speed of light to infinity, it's going to go back to the Poisson equation. So this limit is killing the life of phi. And all this gets very, very confused once you dig into it. I know that Andreas slightly disagrees with me because he thinks that this thing still has a life of its own, but maybe he'll talk about it in his own talk. So the debate is still evolving around this idea that whether there is a mediating system or not, what are the true degrees of freedom, and how gauge invariants complicate things. We know that nobody can really write these true degrees of freedom. They depend non-locally on matter, and so on. Which takes me now to how quantum reference frames could help in this story. In this paper, we have a small prototype example of a use of a quantum reference frame, which makes the point that if you do this quantum controlled diffeomorphism that also Czeslaw was talking about, on each branch, you can isolate the degree of freedom that is in a superposition, which is the distance in each branch, which is the invariant thing, the diffeomorphism invariant thing in each branch. And notice that this is a non-local degree of freedom. It's not at a point, all right? Another prototype example, which is what Czeslaw was talking about, this paper with Anne-Catherine and Victoria, is that you can define definite or indefinite causal order in this game of quantum controlled diffeomorphism, what is invariant under quantum reference frames, if you want. And this other prototype example is also a non-local thing, because proper time is, again, not defined at a point. You need 2 points. And you need a curve that connects them. So let me bring another thing in the game, which is that if you've been through a trajectory of quantum gravity, you know that there is a horrible problem in gravity which goes to the classical theory. It doesn't have anything to do with the quantum theory, which is a problem of observables, which is essentially that this group, diffeomorphism group, is just horrible. It's immense. Nobody knows how to define it. Well, you know how to define it, but you don't know how to, manipulate it. And there is this very cute paper that we wrote with a friend a few months ago. It's also a letter, which is very theoretical, is with this abstract field of mathematics called descriptive set theory. But it shows that somehow the reason that you cannot find these observables that are invariant under this huge group is because it's impossible. They are not definable mathematically, essentially. They are not definable in any algorithmic way or any analytic way that you could imagine. You have to use the axiom of choice to say they exist in some sort of theological manner, and that's it. So how do you put all this together? Well, first of all, I think we should de-obsess ourselves about trying to find observables that are local and think about global observables. The second is that we should think in the discrete, so bring graphs in the game. Think about coordinates as names instead, and changes of coordinates are renamings. This relates to a paper with Arrighi. In which case things are going to be definable now, and explore quantum coordinates and reference frames in this setting, which would also be more amenable to a known theory, quantum gravity, which has under control the notion of quantum space, and test these ideas. So this is pretty much the direction in which I'm going, and I see the things I'm doing to relate to each other. And I leave you with a quote from my PhD supervisor, and that's it.
Great, Marius, thank you. Do you have any questions?
Yeah, could you comment a little more about this last theorem that you showed? I mean, what exactly does what exactly?
So take the space of false solutions of Einstein's equations.
Okay.
Think of functions from that space of solutions.
Space of S is the space of solutions of the Einstein equation.
Yes. R is some space in which they're going to take values, which can be very generic. It's called Polish space. Just imagine anything you can imagine. And ask if that R can be definable in any analytical way, while demanding that this observable is complete, meaning that if I give you two diffeomorphically inequivalent solutions, it can tell them apart. It's going to take different values in this R. And the answer is that you cannot have both. You cannot have them both complete and definable.
So, but just to understand, this S then is the set of Einstein's. So it's basically any solution of Einstein's equations.
If you take all solutions, it's very easy to get it. The striking thing is that you get it in vacuum as well.
Okay.
Yeah.
So it's already in vacuum.
Already in vacuum. Yeah. I mean, I didn't say because I didn't want to go into it, but that's the main point, that you get it in vacuum.
Other questions?
Well, if there's time. I'd like to hear about your personal view on these. You mentioned very briefly, because it's something which is usually known, that you cannot make superposition of different charges, states with different charges. But usually we consider different mass superposition of masses in different positions, or
you can make
different masses like internal energies or something like that. And basically they are the origin of these two conservations principles actually are very similar. So why there's no like super selection rule associated to, for instance, masses and position of mass, center of masses, as we usually assume that there is for electromagnetism, and
I don't know why there isn't one, but
because it's usually, I don't see the difference actually, apart from the fact that gravity is much weaker than probably from the observational point of view, maybe it's more easy to obtain this superposition of masses without keep coherence of superposition of different masses, but it's not much different than, for instance, superposition of charges, right? So, do you have a personal view why they actually seem to be so different? Why theoretically?
No, I wasn't making any strong statement. I was just saying that if you have a
No, I know.
Yeah.
I just want to. Yes, I know. I just want, because since you have worked with this kind of things, I just wanted to see your.
I was speculating on what could be an interesting direction to go, and in relation in particular to this work of superposition of rotations,
Right, yeah.
where you have rotational energy and you use mass energy equivalence to bring in really the speed of light. And that's something that is somehow, I cannot think of an electromagnetic analog, that's all I was saying. Yeah, the other questions I'm not sure I follow them. I don't have any deep reason why we don't, have superposition of charge in electromagnetism and in gravity. It should be possible, but we should also, we haven't seen that, but we suspect.
Yeah, but we've seen. I think that isn't fair to say that we have seen superposition of masses when we, for instance, have an atom in different energy levels, superposition of different energy levels. That's superposition of mass, right?
Well, no, you have to see it gravitating, right?
Yeah. No, I know, yeah. But we have the superposition of masses. We didn't measure the gravitational, but we believe that we can have that. But for charges, usually it's considered that it's impossible. And
that's right. That's right. Two things. One is different to believe and different to know. The other is I don't know why you don't. I don't have an answer to that. Why you do not have a super selection rule in gravity? I don't know.
So if there are no more questions, thanks again, Marius.